Hello, I'm John Reuben from the Chair of Computer Architecture, and in this video, I give a brief introduction, a sneak peek into this book, Resistive RAM and Peripheral Circuitry. Um, so, we all know about flash memory. Flash memory is basically a floating gate transistor. It's a dominant non-volatile memory in the last decade, and it has got a structure which is very similar to a MOSFET. Um, but in addition, the MOSFET has a metal oxide and a semiconductor, but we also have what is called as a floating gate. And here we have charge trapped in this, and once it's trapped, it stays there for 5 to 10 years, 10 years. Um, so these cells are arranged as in two-dimensional rows and columns, and also built as 3D, and that's how you've got this your solid state disks and your pen drives used in your computers. Um, so why do we need new NVMs at all? Because this book is about resistive RAM, it's an emerging non-volatile memory. Um, that's because there are a few limitations identified by um, IRDS, is the International Roadmap for Devices Systems. So they've identified um, a few problems with this flash memory in the near future, about the endurance and the erase time being high, and the high operating voltage, almost 15 millivolts. And also, if you see the memory hierarchy in the past, so you have the on-chip cache, which is made of SRAM, and the main memory, which is dynamic random access memory. The access time of DRAM is around tens of nanoseconds, 30 to 40 nanoseconds. And then you have the storage memory, which is basically your solid state drives, NAND flash based, or your magnetic hard disk drive, which have access time of hundreds of microseconds to even milliseconds. So if you see that there is a gap, we could have some memory with some access time of 100 nanosecond. And so you also have a gap here. On chip cache could be accessed in less than 10 nanoseconds, and you could have some memory. And some of the non-volatile memories does offer this possibility of accessing in nanoseconds. So you could have some non-volatile memories filling this gap. I'm going to talk about them, and specifically about DRAM. And so they could either be embedded on chip, or they could be off chip. So these are the emerging non-volatile memories researched in the last decade. So broadly, you could classify them as either resistive switching memories, or ferroelectric memories. So in the resistive switching memories, the data is stored as resistance, and so that's why they're called resistive switching. They switch between a low resistance state and a high resistance state. And you have a resistive RAM, where the change in resistance is because of a formation of a conductive filament or a rupture of it. And you have phase change memory, and you have spin transfer torque, magnetic random access memory, and of course you have ferroelectric memories. Again, you have three flavors. One is not shown. One is ferroelectric RAM, which is a one transistor, one capacitor, with the capacitor is a ferroelectric capacitor, or it could be a ferroelectric tunnel junction, where a ferroelectric layer is sandwiched, very similar to a ReRAM, but instead of having a metal oxide, you have a ferroelectric layer. Or you could have a structure called ferroelectric FET, where very similar to a flash memory or the floating gate transistor, you have a ferroelectric layer here. But this book is going to only talk about this. So uh, resistive random access memory. So the title of the book is Resistive RAM and Peripheral Circuitry, and the subtitle is An Integrated Circuit Perspective. Okay, that's important because this book is giving a circuit perspective. It's not about device physics, although there are a lot of other books on ReRAM device physics, switching mechanism, and all that stuff. We do discuss the basic device switching mechanism, and any circuit designer should have a basic understanding of the device, but not so much in detail at the ion level. And basically, the book has got three parts. The first part is more into the device and modeling and the array structure. How are these devices integrated, and to form an array, and the second part is about the peripheral circuits around the memory array. It's got three chapters, 5, 6, and 7, and the last part is about in-memory computing, because that is the trend now, that we want to move computing to the memory, because of the von Neumann bottleneck. So I quickly go through the three parts, and each chapter, just a quick view. So after chapter one deals with introduction to the book and what I have discussed so far about the whole memory landscape and the circuit emphasis of the book, and then I start with chapter two with the device structure. So this is the general structure. It's got two electrodes and switching material, but industry identifies two different types of RAMs. One is the oxide RAM, and another is the conductive bridge RAM. These two are different in the structure in terms of the switching material being either metal oxide or solid electrolyte, and the switching mechanism. So I talk about it not in detail. The difference is that this switches by valence change mechanism and this switches by electrochemical metallization. And so really the switching between the high resistive state to the low resistive state and back from low resistive to the high resistive state is because of the formation and the rupture of this conductive filament. And I discuss about properties like endurance, which is the number of cycles the device can be switched between two resistive states, retention, how long can the device retain the state, the variability. When you read from two different locations in the memory, if both the devices are programmed to high resistive state, but you read it, the currents are a little different. So that is the device to device variability. And the cycle to cycle variability is that the device is in high resistive state, you program it to low resistive state, again you program it to high resistive state, and you read high resistive state, and the value is different. Initially it was 3.5 microampere, now it's 2.5. So that is cycle to cycle variability on the same memory location. So chapter 2 really deals with all these device characteristics. So I start with the structure, composition, the switching kinetics is how fast the device switches, and the switching energy. That is very important because we have to know the switching energy forms a fundamental aspect. If to switch a single device, memory device, you take a lot of energy, then your whole memory array is going to take a lot of energy, and so it's not going to be a very energy efficient memory array. And endurance, retention, and variability, how is it measured, how is it reported? Chapter 3 is important. It goes to modeling. So basically the thing is, in CMOS, we, once the technology was mature, we had models. We have the SPICE models, BSIM models, and we used them in the circuit design in Cadence Virtuoso to design circuits. And so similarly for ReRAM, we have got models, and a lot of models have been proposed. But this book, we discuss Stanford PKO ReRAM model. Why? Because it's a physics-based model and it's compact. It's compact, so it's most suited for circuit designers, because circuit designers, you will be simulating an array with the peripheral circuit, and you'll be studying something. You'll be studying the energy consumption of reading or writing, or you want to do some in-memory computing. You want to simulate a small array or a large array. So you need to have a compact model, which is kind of an approximation. Doesn't go so much into depth. So the simulation time must be less because you're going to simulate, who knows, a 256 by 256 memory array. So the Stanford PK model is a compact model for RAM. So this is the basic skeleton. So the current through the device is expressed as a sine hyperbolic function of the voltage across the device. This exponential term implements a sudden increase or the decrease in current. But what this chapter discusses is that, how to, given a ReRAM specification, how to tune the parameters of this model to mimic this. So because different ReRAM manufacturers, their devices have got different characteristics. By characteristics, I mean the low resistive state or the high resistive state, the set voltage, the reset voltage varies from device to device. So this is a fitting algorithm. So chapter 3 discusses this. So as I said, chapter 3 basically, to give a overview, the approaches to modeling, Stanford PKU model and the fitting algorithm, and steps to simulate it in the Cadence Virtuoso. Chapter 4 deals with array configurations. Broadly, there can be two broad classifications. One is 1T, 1R, and the other is 1S, 1R. So in 1T, 1R, the ReRAM device is fabricated on top of the drain terminal of the transistor. So the transistor functions as an access device, but also as a current limiter. So it enforces a current compliance. I talk about it in detail. And the other configuration is 1S1R, where instead of an access transistor, you have a selector device. And the difference is area. So both are trade-offs. So 1S1R is competitive because it has got an area of 4F square. Again, I talk about F and how it is 4F square um, in the book and in detail. And here it is 1T1R. So 1T1R, each memory cell occupies approximately 15F square to 30F square. So this is goes down on memory density. But then this is more reliable because we don't have what is called as um, this selector problem. Basically, we have a problem called sneak path. Again, I have discussed it in the book, and that is because we are not able to access an individual memory cell without affecting its neighbors. And so it is customary to integrate a selector device which has got an IV characteristic like this. And so if your resistive RAM has got a characteristic like this, and if you integrate a device whose IV characteristic is like this, along with the device, and the total IV characteristic is going to be like this. So this is the IV characteristics of a 1S1R device. So basically what happens is if this is the voltage at which you write, and if you take half the voltage of it, the current is so less. But this was not the case if you had a single ReRAM. So basically, this is going to help you to achieve energy efficient writing, because otherwise you will have sneak path currents. So I talk about sneak paths and 1S1R array and the types of selectors. Um, so I discuss the configuration and the selectors, and then the last part of chapter 4 is three ways to increase memory density. One is by scaling, the other one is by multi-level cell. So in multi-level cell, I discuss how from one high resistive state you could switch it to three different low resistive state, and this is by increasing the compliance current. So the transistor, you vary the gate voltage of the transistor and you have an increased compliance current, and it forms a thicker filament. And there is also another way of achieving multiple resistance state, where you have one low resistive state and multiple high resistive state. And that is because there's a larger gap between the filament and the counter electrode. So I discussed this multi-level cell capability and briefly about 3D stacking um, of the ReRAM. So that is part one. And in part two, we are really going into the peripheral circuitry. So I start with the circuits to read from the array. I talk about general principles of sensing and these three modes: voltage mode, current mode, and time based. So when I talk about each of them, I talk about each of them in detail like this. So how do you connect your sense amplifier to the memory array? What is the internal structure of the sense amplifier? What is the sensing process? So we pre-charge the bit line and we discharge it for a short time, and based on the resistance of the cell, it gets discharged to a slightly discharged, or gets discharged very heavily, and then you have a VREF which is in between them. So all this I talk about in detail. And this is voltage mode sensing. I also discuss about current mode sensing, where the current is drawn out from the ReRAM cell and is compared with another current. And then time-based sensing is similar to voltage-based sensing. Voltage mode sensing, the only difference is that you don't have a reference voltage, but you use time as the reference. And some ReRAM technology specific issues like redisturb, why is it happening, and random telegraph noise. And also there's a design example at the end of this chapter. So chapter 5 is really large with all the details of the sense amplifiers. Um, Chapter 6 is about programming the ReRAM array. So basically about programming circuits or write circuits. So the basic write circuit is something like this. So as you can see here, for the ReRAM to switch, you have to apply a positive voltage across the device. it switches from high resistive state to the low resistive state, and from low resistive state to high resistive state, if you want to switch it, you have to apply a negative voltage. So you have to apply a voltage of opposite polarity across the device. So how is it done? So this is the basic right process. So when you have a set operation, you have the voltage applied to the bit line, source line grounded, and you have the reset process, the voltage applied at the source line and the bit line grounded. And then I expand on it. So how is the voltage regulated? So low dropout voltage regulator can be used. And then because of what we have a problem called variability with DRAM, writing is typically not done in a single step. So there are two approaches to overcome variability in ReRAM. So one is the incremental program and verify approach, where you apply incremental pulses, or you have what is called as a write termination approach, where you terminate the write process once the required resistance is reached. So how do you monitor the bit line current or the source line current and do this write termination? So the circuits for it from the literature. And this is all about 1T 1R, and then I also talk about writing into 1S 1R arrays. So there are some differences, because in 1S 1R arrays, you have the sneak path problem, and you need to reduce the sneak path currents in the other locations of the array where the writing was not intended. So you need to apply V by 2 or V by 3. So those two schemes and the issues faced while writing. And chapter 7 is about the row and column decoders, and also about multi-level cell, and a brief introduction to memory architecture. So again, just to give a sneak peek, it's some schematics like this. How one of the type of decoder is an AND decoder, and how it's used to select the row, and then how pre-decoding is done for large arrays, column multiplexes, and how you could write multiple states, and how do you read multiple states, that is more than two states. How do you read them? Sense amplifier for it, and a little bit into how all these things are put together. So this is the sub array. This is the smallest array, and many such sub arrays form the actual memory array. So this is only 1 kilobit, and how you put all of them together. And part 3 is about in-memory computing. So again, I start with von Neumann bottleneck, and why we want to move data to the memory array. And so the last chapter, part 3, the chapter 8, as you can split it in two parts. One is Boolean logic in memory array. So that is basically a digital mode of computation. So I discuss about the in-memory NOR gate. The basic principle of this is a voltage divider, and so this forms an in-memory NOR gate. And so this output resistor, which is initialized to low resistor state, either switches or it remains the same. And so this is a NOR gate truth table, where the 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 data logic 0 and logic 1 are high resistive state and the low resistive state. And I also discuss about the in-memory majority gate, where if you have the inputs to the majority gate as three resistance programmed here of the 1-to-1 array, and you um, activate all the three word lines simultaneously, and you sense the effective resistance, and you could have a majority gate like this. So the operating principle is that sensing resistance in parallel. And then I also discuss about how 1-bit adders are implemented and how in-memory adders. So here I've shown a parallel prefix adder, an 8-bit parallel prefix adder implemented in memory array. So what we have seen so far is this, the last chapter, NOR logic operation, majority logic, and how 1-bit adders and 8-bit adders. And then finally, I discuss about matrix vector multiplication, which is again another hot topic in the memory community today, and in memory computing community. So this is an analog mode of computation. So it's estimated that 60 to 70 percentage of all neural networks have what is called as this matrix vector multiplication. So this matrix multiplied by this vector. and typically it's done using multipliers. You have the weights multiplied with the inputs, and then you add it, you accumulate it, so you have a1 as x1 w11 and so on. But here how it is done in the memory array is that um, the inputs are transformed to voltages using a digital to analog converter applied as voltage, and the weight matrix is written as conductance of the memory array. And according to the conductance, you're going to have a current which is going to get summed like this. And then what you have, if you have an analog to digital converter at the output, you will get an equivalent of this sum as A1, A2, A3. So this is the basic concept. So I would discuss that. And so that's it about this book. And this book is available um, all parts of the world in these bookshops, leading bookstores and distributors. And an ebook will be available in early 2020-25. Thank you.